Recall that for inverse functions, f of f inverse of x equals x. That was one of our tests to see if we had inverse functions. And f inverse of f of x equals x. That was the other test. We are taking the compositions of functions to test to see if we have inverses. Well, let's apply that to our inverse sine, inverse cosine, and inverse tangent. So look what I've written here. If x is between -1 and 1, and y is between -pi/2 and pi/2, well, -1 and 1, that sounds like a ratio to me. And between -pi/2 and pi/2, sounds like that's in radians. What do we measure in radians? That's the angle. So I'm going to make a few statements here. One is that sine of inverse sine of, well, when we see this inverse sine, we're trying to find the angle. So we take inverse sine of the ratio, and the ratio is x. Well, if this x is between -1 and 1, and the output is between -pi/2 and pi/2, then this will simplify simply to x. How about the other way? What if we did inverse sine of, well, we take sine of an angle. Oh, here's our angle, y. Well, if y is in that range, then inverse sine of y is simply y. So you can see, under the right conditions, if the ratios between -1 and 1, these two sort of just cancel each other out. They undo each other. And if our angle is between -pi/2 and pi/2, they also undo each other. For the cosine function, using the same idea of inverses undoing each other, if our x is between -1 and 1, well, -1 to 1, that sounds to me like a ratio. And y is between 0 and pi. What do we measure with pi's? Oh, that sounds like radians. So this must be an angle. Then we can conclude that cosine of inverse cosine of, I'm just using this principle right here. Well, we take inverse cosine when we're looking for the angle. So we take inverse cosine of the ratio. So cosine and inverse cosine, they undo each other, and we're left with x. And how about inverse cosine of, well, we take cosine of an angle. Oh, here the angle is y. So as long as y is between 0 and pi, then inverse cosine and cosine undo each other, and this simplifies to y. But we've got to make sure the conditions are right. What about if x is a real number? Well, in our previous examples, x was the ratio. So the ratio can be any real number. And the output, y, is the angle. Well, we're going to use this inverse principle here and say tangent of inverse tangent of, well, I'm looking for the angle when I have that little -1 dangling in the air. So I must be taking the inverse tangent of the ratio. If this ratio is any real number, then this will simplify to x, because the tangent and the inverse tangent will undo each other, just like we talked about in the general principle. What about inverse tangent of, well, we take tangent of an angle, and here our angle is y. As long as this y is between -pi/2 and pi/2, look, I have no less, greater than or less than or equal sign. It's just y is greater than and y is less than. So I can't touch -pi/2 and pi/2. This simplifies to y. So I just went over a boatload of rules, and you can learn them, and they make sense, particularly if you look back at the graphs of sine and cosine and tangent and inverse sine and inverse cosine and tangent, particularly the graphs that have had their domains restricted so that they pass the horizontal line test, etc., 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 etc. And that makes sense. Or you could learn two simple rules. They are work inside out and draw two circles.